Hello everyone, welcome to my channel C Patel Metallurgy. We have come with GATE 2020 solutions, and the first we are going to see about physical metallurgy. And in physical metallurgy, let us see first the 1 marks question. So question number 3. A slip system consists of a slip plane and a slip direction. Which of the following is not a valid slip system? Okay. Which of the following is not a valid slip system in FCC crystal, copper crystal? We know a slip system should have slip direction, right, and slip plane. Okay, suppose this is a plane, slip plane, and direction is like this. The direction will lie on the plane. So the plane normal, this one, and the direction will have angle of 90. So whenever there is angle of 90, suppose this is n vector and slip direction is a vector, then n dot a vector should be what? 0. What? So we'll apply this logic. Okay. So here in the case of FCC, you see the first case 1 1 1 and 1 1 bar 0. So 1 multiplied by 1, so plus 1 into, that is minus 1, plus 0, that is 1 minus 1 0 is equal to 0, right? In second case, 0 plus 1 plus 1, that is 2, it is not 0. So here only the value is not 0, so option B will be the correct answer. But let us see other options also. 1 1 1 plus 0 plus minus 1, so this is also 0, right? Here last one, 1 plus 0 minus 1, so this is also 0. So what is the answer? Answer B. Next question. A dielectric material is, what is a dielectric material? Is it an electrical insulator, metallic magnet, two coupled electrical conductors, or electrical insulator? We know a dielectric material is nothing but a electrical insulator. Okay, so what happens? There are two metal or dielectric material which are kept parallel, and we apply some current over there. Then what happens? That some charges develop, positive and negative, according to the condition what we have applied, right? So opposite charges develop. So these opposite charges are developed, and this is the property of an electrical insulator, that is a dielectric material. Okay, next question. Angle between two neighboring tetrahedral bonds in silicon having a diamond cubic structure is sorry. So here we are having tetrahedral bonds. So if you draw the tetrahedral void or bond, then we'll get something like this. Okay, and what is this angle? This angle is 109.5 degree. So there is derivation of this also. So right now we are not going to discuss about the derivation because it is just a 1 marks question. So you simply remember this, the angle is 109.5 degree. Okay, so answer B. Question number 15. The sequence of precipitation during aging of aluminum 4 weight percent copper alloy A. Okay, so what is the sequence of precipitation? If you draw the aluminum copper phase diagram, so it look like something this, right? Sequence of precipitation during aging. So when aging takes place means with time, copper, which is dissolved, copper here it is in dissolved state. when we quench it, it is again in dissolved state. But if you see the phase diagram here, so this is the equilibrium phase diagram where we should have some copper, that is alpha, okay, plus aluminum matrix, okay, right? So here we need to have two things, so which we don't get after quenching. So with time the second phase starts to build up, and this second phase is nothing but copper. So what are the sequence? The sequence is, first is the GP zone, right? Second is theta double dash, then theta dash and theta. So if you see the diagram, that is strength versus aging time. The strength increases as the GP zones form. GP zones forms up to this layer. Then theta double dash, okay, then theta dash, then here theta. So when theta forms, that is nothing but CuAl2, complete CuAl2, and this decreases the strength. So you remember here the current sequence is of option A. Okay, so the next question is the number of atoms per unit area in one OO plane of PB is. Okay, here the crystal structure of PB is FCC, right? Let us draw FCC first. This is FCC having these are the atoms, then face entire atom, okay. Here we have been asked about one OO plane. So one OO plane is nothing but the surface plane. You can consider this plane or any surface plane, okay. And here the radius is given as 0.175 nanometer, right? Okay, so here it is asking the number of atoms per unit area in one OO plane. Suppose let us consider this plane, one OO plane. So we need to find first the area. So for area we require edge length, right? And we know in the case of FCC that radius is nothing but root 2a by 4, right? So here we'll put radius, that is 0.175, and we will calculate A. Okay, so A we will get as, I have calculated this one, 0.49 nanometer. Okay, now we have to calculate the atoms per unit area. Okay, so what is the total number of atoms on one OO plane? This is the complete atom, 1 plus, and the 4 corner atoms, and these are shared by 4 faces. Okay, so 1 plus 1, that is 2, right? Okay, so atoms per unit area, nothing but 2 divided by area, that is 0.49 into 0.49, that will be equal to 8.32. Right, this is the answer. Now question is question number 34. X-ray diffraction pattern from an elemental metal with a FCC crystalline structure shows the first peak at a Bragg angle of theta 24.65 degree. The lattice parameter of this metal is, okay, and here it is given the wavelength of X-ray used. So this is a problem of Bragg's law. So we know here lambda is equal to 0.1543. We know lambda is equal to 2d sin theta, right? Yeah, lambda is equal to 2d sin theta. Okay, so lambda is equal to 2, d is nothing but a divided upon h square plus k square plus l square to sin theta. So here it is given first peak. So first peak comes when h square plus k square plus l square is equal to what? 3, right? So we'll put these values. So lambda is equal to 0.1543 to a, we have to find h square plus k square plus l square is 3, then sin theta, and theta is what? Bragg angle. So Bragg angle we are given here 24.65 degree. If you solve this question equation, then a you will get as 0.320 nanometer. So this corresponds to option C. Right guys? Let us move to next question. This is a match type question. So question number 35. Match the materials in column 1 with their common applications in column 2. So column 2 is applications and this is material. First one is gray iron, ductile iron, then zirconium alloy, then beryllium copper alloy, right? So gray iron, if you see the application, cladding for uranium fuel in reactor, nuclear reactor, base structure of heavy machines. We know base structures should have high damping resistance, right? And damping resistance is better in gray iron, that is gray cast iron. So P will match with 2, right? Then valves and pump body. If you see the valves and the pumps, then these materials should be somewhat soft, right? Somewhat soft because these valves and these are very intricate shapes and pump bodies. So this should be, we manufacture using extrusion process and other processes like this. So this should be somehow, have some ductility in it. So ductile iron will be used. Next is zirconium alloy. So zirconium alloy will be used for the cladding purposes because this helps in some absorption and these things. Then beryllium copper alloy. Beryllium copper alloy is used in jet aircraft landing gear bearings. Why beryllium copper is used? Because we know that the copper, when we mix with beryllium, so this strength also we get, right? Strength also we get, and proper lubrication point of view also, that is also very possible in case of this alloy, right? Copper beryllium alloy. We are getting P matches with 2, Q matches with 3, R is 1. P matches with 2, Q matches with 3, R is 1 and S with 4. So option D. Okay guys, so next question. Okay, the MgSN phase diagram exhibits two eutectics on either side of the high melting intermetallic line compound Mg2SN as given below. So these are the conditions. At 561 degrees centigrade, the first eutectic observed, where liquid is changing into alpha and Mg2SN. At 203 degrees centigrade, liquid is changing into beta and Mg2SN. After the eutectic reaction has gone to completion and equilibrium has been attained at a temperature just below 561 degrees centigrade, the amount of eutectic constituent present in the alloy Mg 50 weight percent SN is. Okay, so these are the options with we are given here atomic weights also, right? Okay. Okay guys, so first of all we need to draw this phase diagram. We are given some idea here that Mg2SN is an intermetallic which is forming. So if you see Mg2SN, right, so what will be the composition of SN at which this Mg2SN form? So according to stoichiometry, 2 atom of Mg plus 1 atom of tin is matching and we are getting Mg2SN, right? So what will be the composition of SN? So atomic weight of SN, that is let us say that is molecular weight of SN divided by molecular weight of Mg2 plus molecular weight of SN into 100. This is the weight percent we will get. So SN we are here SN 118.7. Okay, 2 into Mg atomic weight is given 24.3 plus 118.7 into 100. Okay, so if you calculate this one, and this will come around 70.95 weight percent. Okay, so we'll try to draw the phase diagram. At 70.95, this Mg2SN is forming, right? And if you see, the next condition is at 561 degrees centigrade, liquid with 36.9 weight percent SN, right? So 36.9 will be in the left hand side. So suppose this is 36.9. And next eutectic is 97.87. 97.87. So this will be very close to this one, right? Okay. Here reaction is taking at 561 degrees centigrade in the left hand side. So 561, let it be here. And the right hand side it is taking at 203. So let it be 203, right? Okay. So this will be somewhat like this. What? The phase diagram would look like this. Okay, and here again read the condition. After the eutectic reaction has gone to completion and equilibrium has been attained, the amount of eutectic constituents present in the alloy 50-50% is approximately. Okay, so we have to find at 50-50. So 50 composition would be here, suppose. Okay, Okay, so here is the liquid, and here we are getting, it will be somewhat like this. Okay, so here we are getting alpha plus Mg2Sn, right? Mg2Sn is the eutectic product at 36.9 we are getting, and here also we are getting the same thing, that is we are getting beta Sn and Mg2Sn, right? Beta plus Mg2Sn, right? So in the question it is asked the amount of eutectic constituent present in the alloy Mg 58% SNE. So Mg 58%, this one. So we are here, it has been asked for the left hand side case. Okay, and since the eutectic composition is to be known, so we will take the tie line between this point A and point B, and this is the point C at 58%. So percentage here in the left hand side it will be eutectic composition, and the right hand side it will be Mg2Sn, right? This one. So percentage eutectic composition will be what? Cb divided by AB into 100, right? So Cb is what? 70.95 minus 50, and this total will be 70.95 minus 36.9, right guys? So if you calculate this one, let me do the calculation here, and you will get that this will be around 62 weight percent. I've done the calculation, and this will be around 62 weight percent. So 62 weight percent is nothing but option C. Okay, so you know, or did you understand that this type of problem needs to first draw the phase diagram like this, and after that you will be able to comfortably calculate the phases. Okay, next question is a match type question. Match the elements in column 1 with their electronic behavior given in column 2. Okay, so first one is copper, then iron, then mercury, then silicon. Ferromagnetic, superconducting, semiconducting, diamagnetic. So ferromagnetic means magnetic material. So ferromagnetic is nothing but iron, it will be fine. Superconducting we have mercury at 4 Kelvin, below 4 Kelvin. Semiconducting, we know silicon is a semiconductor. Then diamagnetic means which does not attract with magnet. So this is copper. So P4 Q1 R2, P4 Q1 R2 S3. So option C here, right? Okay. Now let us move to next question. Radius of the largest interstitial atom that can be accommodated in an octahedral void in BCC iron without distorting the lattice is, okay, rounded off to 3 decimal places. Assume hard sphere model and radius of iron atom is 0.124 nanometer. Right. So here it is being asked about the octahedral foil. We know that iron has got BCC structure. Let us draw BCC structure first. These are the solid iron atoms at the corner and at the body center, right? So this will be at body center, this one. Now there will be one more unit cell at the above, right? So there also will be one body centered atom, right? So if you join the lines between them, okay, so this is nothing but a octahedral, okay, and the octahedral void will be present at the center of the surface, right? Will be present at, this will be the octahedral void, right? So here it is asking about the maximum size of the atom which can be accommodated in the octahedral void. So if we calculate the length, the side length, so this is what A, right? This is what root 2A by 2. Okay, this is A. This is what root 2A by 2, right? And what will be this height? This height will be what? A by 2. Okay, so this is A by 2, and this is what A, this length is A by root 2, that is equal to A by root 2. So among A by root 2 and A by 2, which is larger number? So this is larger number. So this will be separated. Basically, this will be separated, and these atoms are separated by a larger distance as compared to the atoms which are on the top. Like if you consider this phase, then these atoms 1, 2, 3, 4 are separated by a larger amount as compared to the atom which are at these two positions, 5 and 6, right? So the deciding factor for the deciding factor for the size of the void, or the size of the radius of the atom which can be fitted in this void, will be determined. So here guys, this A by 2 length will be what? This is your capital R and this is your small r, that is radius of the octahedral void, right? So this will be A by 2 equal to R plus R. This means R plus R equal to A by 2, and A in the case of BCC it is 4R by root 3. So 4R by root 3 into 2. So R is equal to, this will be what? Capital R. So R minus 2 by root 3 R is equal to small r. So R 1 minus 2 by root 3 equal to R. So if we calculate this one R, it will come 0.019 nanometer, right? So this will be the answer. Okay guys, so next let us move to the next question. Zone refining of silicon results in residual P content of 0.1 parts per billion by weight. The electrical conductivity of this zone refined silicon is this. Okay, the given things are Avogadro number is this, density of silicon is this, atomic weight of phosphorus is this, charge of electron is this, mobility of electron is this. So this is a problem of conductivity in the case of external semiconductor, where we are adding some amount of P. We know that silicon has 4 valence atoms. Okay, so if we try to add phosphorus over here, then since phosphorus has got 5 electrons, so 1 electron will be free, and this helps in what? Conduction. So it becomes more conducting. Okay, and here in the case of this alloy, it is what? The concentration of phosphorus is 0.1 parts per billion. Okay, so we will use this concept later on. And here, okay, that guys, we know that density is nothing but number of atoms, molecular weight, Avogadro number into volume, right? So from here we'll calculate N by V, that is rho into Na by molecular weight. So rho is what? 2.33, okay, gram per cm cube. 10 power minus 6, it will be converted into meter, right? Avogadro minus 6.02 into 10 power 23. Molecular weight is 30.97. It is in grams, so gram will be cancelled, right? So this will use to calculate the conductivity. We know that conductivity is what? Number of atoms per unit volume into charge of one electron into mobility. So this we will put here 6.02 into 10 power 23, 10 power minus 6 into 30.97, right? Charge of electron 1.6 into 10 power minus 19 into mobility. Mobility is what? 0.2. Okay, this is for this is for the total number of atoms, but here we have what? We have 0.1 ppb of atom. That means for 10 power 9 atom of silicon, right, we have 0.1 phosphorus. So for this n by v, for these n by v atoms will have what? N by v times 0.1 divided by 10 power 9 number of atom, right? So this will be, the next question will be what? 2.33 into 6.02 into 1 power 23, 10 power minus 6 into 30.97, 1.6 into 10 power minus 19 into 0.2 into 0.1 divided by 10 power 9, right? So this will be the conductivity, the final conductivity. So if we calculate this one, this will become 0.1449. Okay guys, so this is the answer, and this was the last question of physical metallurgy. So thank you all for listening.